Okay, in the last section we learned how to find eigenvalues. Remember that eigenvalue problem is ax equals lambda x, or taking the lambda x on the other side, a minus lambda I x equals 0. You're trying to find non-zero solutions, trying to find eigenvalues lambda such that this has a non-zero solution. It'll have only the zero solution unless a minus lambda I is singular, i.e. unless its determinant is 0. So you find the eigenvalues by setting the determinant equals 0. You get a characteristic polynomial of degree n if it's an n by n matrix, and the roots of that characteristic polynomial, which could be complex, are the eigenvalues. But now we're going to talk about how to find the eigenvectors. Well, once you found the eigenvalues, a particular eigenvalue, you want to find the corresponding eigenvector. You simply plug in that value of lambda and solve this system, and you know it's going to have non-zero solutions because the lambda is chosen so that this has non-zero solutions, that it's singular, and therefore there are many solutions. So let's take, for example, this 3 by 3 matrix. Subtract lambda from the diagonal and set the determinant equals 0. And earlier we saw that the characteristic polynomial is a cubic polynomial and the roots are 0, 2, and 3. So we can find the eigenvector or vectors corresponding to each eigenvalue. First, lambda equals 0. Simply plug in lambda equals 0 and solve for ax equals a minus lambda I x equals 0. In other words, find the null space of this matrix with lambda equal to 0. Well, we've done that in previous chapters. You reduce it to row echelon form. You know you're going to end up with at least one row of zeros because you know the matrix is singular with lambda equals 0, 2, or 3. In each case, you're going to end up with at least one row of zeros, so you'll have at least one arbitrary coefficient, and get the general solution in vector form, and it'll be constant times one vector plus constant times another vector, etc. If there's only one row of zeros, there'll only be one arbitrary constant, so the solution will be just a constant times a vector, and that vector will be a basis for the eigenspace. The null space of a minus lambda I for a particular eigenvalue lambda is called the eigenspace, and it has at least dimension 1 because there are guaranteed to be some solutions, non-zero solutions, so the set of solutions is at least dimension 1. It might be more than 1. In this case, it's 1. If you reduce this to row echelon form, there's one row of zeros. You have one arbitrary constant. The general solution will be any multiple of this vector. Therefore, that's an eigenvector, or any multiple of it is an eigenvector. You can say this is a basis. This one vector is a basis for the one-dimensional eigenspace for the eigenvalue lambda equals 0. And you do the same thing for each of the other eigenvalues. For example, lambda equal to 3. Just plug in lambda equal to 3 and solve for x and reduce it to row echelon form. Again, you're guaranteed to have at least one row of zeros if that really is an eigenvalue, because the matrix a minus lambda I is singular, and the general solution to that, they're going to be non-zero solutions, so dimension at least 1. In this case, it's also 1, and any multiple of 1, 2, 0 is a solution. So 1, 2, 0 is a basis for the one-dimensional eigenspace corresponding to lambda equal to 3. This is a basis for the one-dimensional eigenspace corresponding to lambda equals 0, and they go ahead and find the eigenspace for lambda equal to 2 also. So finding the eigenvalues is the hard part. Once you found those, to find the eigenvectors corresponding to each eigenvalue is just a chapter 1 problem. You just plug in that particular value of lambda and solve a minus lambda I x equals 0, and we've done that in chapter 1. Homogeneous system, you'll have a solution of a dimension at least 1. The null space of a minus lambda I for that particular eigenvalue lambda will be dimension at least 1, but it might be more than 1. In the last example, we had 3 different eigenvalues. The eigenspace for each was dimension 1. That's called the geometric multiplicity of an eigenvalue is the dimension of the eigenspace. So in the previous example, there were 3 different eigenvalues. Each one had geometric multiplicity 1. The algebraic multiplicity is the number of times that lambda minus that eigenvalue appears in the characteristic polynomial. So for example, if the characteristic polynomial factors as lambda minus 1 times lambda minus 2 cubed, then you say that 2 has algebraic multiplicity 3 and 1 has algebraic multiplicity 1. And notice the algebraic multiplicities always add up to n, the size of the matrix, because characteristic polynomials degree n, it'll have exactly n factors. Some of them may be multiple, but if you count the multiple roots multiply, it adds up to n. Now the geometric multiplicities, well, here's an example where the 3 examples here, three different matrices. A is upper triangular, so you can just read the eigenvalues off the diagonal. There's only one eigenvalue, it's 1. Has algebraic multiplicity 3 because the characteristic polynomial will just be 1 minus lambda cubed. So 1 is the only eigenvalue and it's multiplicity 3. But now let's find the eigenvector or vectors. Well, you subtract 1 from A and you get zeros down the diagonal and 1 here and here. And so this first equation just says x2 equals 0. Second equation says x3 equals 0. So the second and third components are 0. The first component can be anything. So the eigenspace is the set of all multiples of 1, 0, 0. In other words, it's a one-dimensional eigenspace, even though, so the geometric multiplicity of the only eigenvalue is 1. So notice that the geometric multiplicities in this case add up to 1 because there's only 1 and it has geometric multiplicity 1. The algebraic multiplicities always add up to n. N is 3 in this case, but in this example, there's only one eigenvalue. Its geometric multiplicity is 1, so the geometric multiplicities add up to 1. Now here's another example, similar, but again, it's upper triangular, so the eigenvalues are 1, 1, and 1. So again, 1 is algebraic multiplicity 3. Find the eigenvectors corresponding to that single eigenvalue. Subtract 1 from the diagonal, and you just get 0, 1, 0, and the rest of the matrix is 0. So now x2 is 0. At x1 and x3 can be anything. So the general solution to a minus 1i times x equals 0 is two-dimensional. The null space is two-dimensional because you end up with 2 rows of 0 and you have 2 arbitrary constants, x1 and x3. So these 2 vectors form a basis for the eigenspace for the eigenvalue 1. And so here's a case where the geometric multiplicities add up to 2. There's only 1 and it's 2. And finally, C is just the identity matrix. Again, there's only one eigenvalue. Algebraic multiplicity of 1 is 3. Subtract 1 from the diagonal and you get the 0 matrix, and that has null space of all of R3. So any vector is an eigenvector now. So that means a 3-dimensional eigenspace. So now there's one eigenvalue. It has algebraic multiplicity 3 and geometric multiplicity 3. And notice in this example, always the geometric multiplicity was less than or equal to the algebraic multiplicity, but it has to be greater than or equal to 1 or it wouldn't be an eigenvalue. There has to be at least one dimensional eigenspace or it wouldn't be an eigenvalue. So the geometric multiplicity is always between 1 and the algebraic multiplicity. Okay, now I'm going to prove something that we're going to generalize later, but the proof is much more difficult than the general case. But suppose we have an n by n matrix that has only 2 distinct eigenvalues, alpha and beta. And let's say alpha has geometric multiplicity k. That means that it has a eigenspace, k-dimensional eigenspace, and let's say u1 through uk is a basis for that k-dimensional eigenspace. And then the other eigenvalue beta, which is different than alpha, has geometric multiplicity m, which means it has a basis of m independent eigenvectors, W1 through Wm. And what I want to show is that if you put all these eigenvectors together, all k of those corresponding to alpha and all m of those corresponding to beta, the whole set is independent. And to prove that, how do you prove that a set of vectors is independent? You set a linear combination equal to the zero vector and try to prove that all the coefficients have to be zero. So let's do that. Set a linear combination of the UKs and the WMs to zero. And first we multiply that both sides of the equation by the matrix A, and A times U1 is just alpha U1. A times each of the U is just alpha times that U. A times each of the W's is beta times each of those W's, because the W's are eigenvectors corresponding to beta. The U's are eigenvectors corresponding to beta. The U's are eigenvectors corresponding to alpha. So if you multiply both sides by A, you get this. The right-hand side, A times 0 is 0 vector. On the other hand, if we take this equation and just multiply the whole thing through by alpha, we get this, and then we subtract the 2. These terms all cancel because they're exactly the same. These terms give B1 times beta minus alpha times W1 plus ... Bm times beta minus alpha Wm. And then you say, well, we know that the W are independent because they're a basis for the eigenspace of beta. Therefore, all of their coefficients have to be 0 by definition of independence. But since beta minus alpha is not 0, that means all the B's must be 0. And then you can similarly show that all the A sub i's are 0 by, instead of multiplying by beta here, instead of multiplying by alpha, multiply by beta and subtract, and same kind of proof. You can prove all the A's are 0. So we've proven that all the coefficients of the U's and the W's are 0, therefore that whole set is independent. So remember, these are the k independent eigenvectors for alpha, which has geometric multiplicity k. These are the m independent basis vectors for the eigenspace of beta. They're all independent. Put them all together, they're all independent. But notice that that means that k plus m has to be less than or equal to n, because you can't have more than n independent vectors in an n-dimensional space. All of these vectors are in Rn. So you can't have more than n independent vectors, and you've got k plus m, so that can't be more than n. But it might be actually less than n, so the geometric multiplicities can't add up to n or less, but they might add up to less than n. And if the geometric multiplicities add up to something less than n, you call that a defective matrix. Basically, a defective matrix, you could say that every matrix, n by n matrix, has a full set of n eigenvalues if you count, multiple eigenvalues multiply. If lambda minus 4 cubed shows up in the characteristic polynomial, you count 4 3 times. That adds up to n, so it has a full set of eigenvalues, but it may not have a full set of eigenvectors if the geometric multiplicities add up to less than n. Now that proof was assuming there were only 2 distinct eigenvalues. Then we proved that the geometric multiplicities add up to n or less, because they're all independent. All the eigenvectors are independent. To prove that in general, that if you have more than 2 eigenvalues, you can still prove that this complete set of eigenvectors is independent. That is, the eigenvectors corresponding to different eigenvalues are independent of each other, and within each eigenvalue, the eigenvectors for the eigenspace, the basis for the eigenspace, are independent. Put them all together, they're all independent, therefore can't be more than n of them. What we didn't actually prove is that for each individual eigenvalue, the geometric multiplicity is between 1 and the algebraic multiplicity. Obviously, it can't be less than 1, or it wouldn't be an eigenvalue. It has to be at least 1 dimension of the eigenspace has to be at least 1, or lambda isn't an eigenvalue, but it can't be more than the algebraic multiplicity. We saw an example where the algebraic multiplicity, 3 different examples where the algebraic multiplicity added up, it was 3 for lambda equals 1, and in one case the geometric multiplicity was 1, another case it was 2, another case it's 3. It can be anywhere between 1 and 3 if the algebraic multiplicity is 3. Homework in section 5. There are some matrices here, and they give you the characteristic polynomials, so they give you the eigenvalues and the corresponding multiplicity. There's a typo here, that should be a minus, for example. Okay, for example, the characteristic polynomial for this 4 by 4 matrix is lambda plus 2 times lambda minus 2 cubed, so that means minus 2 is an eigenvalue of multiplicity 1, 2 is an eigenvalue of multiplicity 3, 3 plus 1 is 4, and for each of those 2 eigenvalues, minus 2 and 2, you're supposed to find the eigenspace. For the eigenvalue minus 2, you know that it's going to be exactly geometric multiplicity 1. You'll have exactly 1 row of zeros when you reduce it down, exactly 1 arbitrary constant, because the geometric multiplicity of minus 2 has to be at least 1, and it can't be more than 1 because that's the algebraic multiplicity. For 2, you subtract 2 from the diagonal and solve, and you might get anywhere between 1 and 3 arbitrary constants in the null space. Okay, the next section is about complex eigenvalues and eigenvectors. We know that a real matrix has a real characteristic polynomial, but the roots of that real characteristic polynomial may be complex, and of course they always will occur in complex conjugate pairs. For example, this 2 by 2 matrix, you get a quadratic equation for the characteristic polynomial. You can't factor it, so you use a quadratic equation, and the roots are 2 plus or minus I. They will always occur, if they're complex, they'll always be in complex conjugate pairs. Now, how do you find the eigenvectors? Well, exactly the same way as the last section. Nothing different whatever, except you're going to have to deal with complex arithmetic, which makes it a lot more complicated, but in theory it's not at all different. You basically take one of the eigenvalues, 2 plus I, and subtract that from the diagonal and solve the system, and same as always, but you're going to get complex eigenvectors, or you might get complex eigenvectors. So if the eigenvalues are real, you're guaranteed to get real eigenvectors, but if the eigenvalues are complex, you're normally going to get complex eigenvectors. And there's nothing different. Everything we said in the last section is still true, just that you're going to have to deal with complex arithmetic, which is not much fun. So I'm going to assume you can do complex arithmetic. It's basically all in the world you have to do is just treat it like ordinary algebra, where I is just another letter, except that remember that I squared is minus 1. And one important trick is that when you divide by a complex number, that is a mess. What you're going to have to do is multiply and divide by the conjugate. So if you got a 1 minus I in the denominator, you need to multiply and divide by 1 plus I. Why? Because 1 minus I times 1 plus I will be real. You don't want a complex number in the denominator. That's terrible. So you can make it real, and then now you can reduce it to 1 plus I. So that's important in your arithmetic. Otherwise, it's just like normal algebra. Just carry the I along as if it were an X or an A. But remember that I squared is minus 1. So your eigenvectors are going to be complex if your eigenvalues are complex. But one good thing is that if you find, I've said the eigenvalues always appear in complex conjugate pairs. You know, if alpha plus beta I is an eigenvalue, so is alpha minus beta I. And the good news is, even though the arithmetic is a lot worse, once you find one eigenvector for alpha plus beta I, then the eigenvector for alpha minus beta I is just the conjugate of the eigenvector. So you really only need to find one eigenvector for each conjugate pair, because the other one is just the conjugate, as they show here. If ax equals lambda x, then ax bar is equal to lambda bar x bar. So if lambda is an eigenvalue, so is lambda bar. Remember, conjugate just means change the sign of the complex part. So if lambda is an eigenvalue with eigenvector x, then lambda bar is the other eigenvalue, and its eigenvector is just the conjugate of x. So you just change the sign of the imaginary part of each component of x. So at least you really only need to find one eigenvector for each complex conjugate pair. Another important result is that a symmetric matrix, that's where A equals A transpose, then it's guaranteed all the eigenvalues are real. So you don't have to worry about complex arithmetic if A is symmetric. Actually, you had a problem in section 1, I believe, where for a 2x2 matrix, you actually proved that the eigenvalues have to be real for a symmetric 2x2. That's true for a general n by n symmetric matrix. The eigenvalues are real, so you won't have to deal with complex arithmetic there. And this example is important because in the real world, you're not going to be finding eigenvalues and eigenvectors of a large matrix. You're going to be using some technology like MATLAB, and so here's a demonstration of how MATLAB can find all the eigenvalues and the eigenvectors for any size matrix. Here's a 4x4 matrix. All you have to do to get the eigenvalues and eigenvectors of MATLAB is the following program. I hope you can read it. It's kind of dark, but EIG is the MATLAB eigenvalue function. So EIG of A, and you give it two matrices to hold the eigenvalues and the eigenvectors. The D, the second one, will hold the eigenvalues down the diagonal. Notice that there are two complex conjugates and then two real ones. And then it gives the columns. This is eigenvector corresponding to this eigenvalue. This is eigenvector corresponding to this one. This is eigenvalue vector corresponding to that. Notice that the real eigenvalues have real eigenvectors. The complex eigenvalues have complex eigenvectors, and they're complex conjugates. That is, this is just the conjugate of that. And they're normalized to have each vector norm 1. You can multiply any eigenvector, remember, by a constant, and it's still an eigenvector. They just divide by the norm to normalize it so you can compare with other results. So finally, the homework in section 4.6. In theory, it's not any different than what we did the last section, but it's going to be complex eigenvalues and therefore complex eigenvectors. So in practice, it's going to be a lot more difficult. Here you're going to, for example, you're going to get a polynomial degree 3, and finding the roots of a polynomial degree 3 is going to be difficult, but they give you a hint. I think they give you one eigenvalue. So if you know one eigenvalue, you can factor. If you know that 3 is an eigenvalue, you can factor out lambda minus 3, and you'll have a quadratic, and you can use a quadratic equation, but it's going to be difficult. Anyway, you're supposed to find the eigenvalues and eigenvectors for a 3x3 matrix. It's going to be a fair amount of work. Going to have to practice your complex arithmetic. In fact, some of the problems are just practicing doing complex arithmetic.